Swayam Prabha. Digital India. Educated India.
Good morning to all of you. I welcome you all to the second lecture on the topic Zeroth and first law of thermodynamics in the subject thermodynamics and thermal engineering. Before we get into the lecture number 2, let us have a recap. Before having the recap, myself Dr. Jawahar, Professor and Dean, Faculty of Technology from Kalinga University, Naya Raipur in the state of Chhattisgarh. So in the lecture number 1, we have discussed about the what is the basic concept of thermodynamics, how it has evolved, a brief history of thermodynamics, what are the types of systems. We have studied about open system, closed system and isolated system, how the system is separated from the surrounding by boundary, what are all the types of processes. Under the types of processes, we have seen constant volume process, which is isochoric, constant pressure process, isobaric, constant temperature process, isothermal. Then the fourth process which we have discussed is adiabatic process, and finally we have studied about the isentropic process. So isentropic process, of course, it is an ideal process. It is not in the real time application, it is for a ideal case condition only. Then we have solved some numerical problems based on this one. In the lecture number 1, we have seen very clearly that the behavior of a system, behavior of any system depends upon the properties of the molecules, because any substance or any object comprises of large number of molecules. Now let us get into the lecture number 2. We will study about the second law, the first zeroth law and first law of thermodynamics before studying the second law of thermodynamics in the next lecture. The contents of my presentation in this lecture is properties, state, equilibrium, process, cycle, zeroth law of thermodynamics, first law of thermodynamics, and some numerical solved problems. How to define a property of a system? So yesterday we saw what is a system. System is a region in a space upon which the attention is paid. Like for example, if you take a piston cylinder arrangement, if if we are focusing on the piston cylinder arrangement, that is considered as a system. Similarly, if the piston cylinder arrangement contains some fluid and our attention is on the fluid rather than the piston cylinder, then the fluid is considered as a system. So that is how the system is described. Now let us see what do you mean by a property of a system. The properties of a system is nothing but the characteristic or features of a system. The characteristics or features of a system is called properties. Examples are, suppose if I denote a state point on a pressure volume diagram or a temperature entropy diagram. Suppose if it is a pressure volume diagram, y-axis is pressure, x-axis is volume. So corresponding to that point, we can find the value of pressure and the corresponding value of volume. Similarly, a point on a temperature entropy plot, any point, corresponding to that point, we can read out the value of the temperature as well as the entropy. So examples of the properties are pressure, temperature, mass, volume, etc. And these properties of a system are further classified into two types: extensive properties and intensive properties. Pressure and temperature are categorized under extensive properties, while mass and volume are categorized under intensive properties. How these extensive properties differs from intensive properties? If you take the extensive properties are the one that does not depend on the mass of the system or the size of the system. For example, if you take a room which has a pressure of say 1 bar, and if you divide the room into 2 equal parts, still the pressure on both the halves will be the same. Or if you take, so let us take the temperature in a room is at 10 degrees centigrade, assuming that it is a winter condition. So 10 degree temperature, degree centigrade temperature is maintained in the room. So, if you divide the room into any number of equal parts, assuming there is no heat loss, every portion of the room will have the same temperature. That is, it is like a thermal equilibrium condition. So, the property which does not depend on the size of the system or the mass of the system. So, that is called extensive properties. So, this pressure and temperature does not depend on the size of a system. Whereas, if you take intensive properties, mass or volume, you take a mass of 1 kg. If you divide into 2 equal parts or 3 equal parts, then the mass gets distributed. The size of the system gets reduced. That means properties which depends upon the mass of the system, which depends on the size of the system, is called intensive properties. This is how the properties of a system having a fixed value, having a constant value is represented. For example, system pressure is 1 bar, temperature is 35 degrees centigrade, mass is, for example, these numbers are just for examples only, 1.5 kg, and volume is mentioned as 0.5 meter cube. Suppose if I divide this block into 2 equal parts, the pressure will still remain same in both the blocks, temperature will remain the same. However, mass will be 1.5 kg divided by 2 and volume also will get halved. So, here I have mentioned 2 extensive properties and 2 intensive properties. Then let us see what do you mean by equilibrium. Equilibrium refers to a state of balance, that means equal values. There are 3 types of equilibrium: chemical equilibrium, mechanical equilibrium and thermal equilibrium. Thermal equilibrium is the one which we will be using it often. Of course, mechanical equilibrium also is there. If the temperature remains same throughout the system, so that means temperature remains constant, it does not vary. So, that such a condition is referred to as thermal equilibrium. That means the system is having equal temperature at various locations in the system. So, that means the system has attained thermal equilibrium. There is no change in temperature. Mechanical equilibrium refers to the state where the pressures are, the system pressure does not change. There is no change in the pressure. And the chemical equilibrium, of course, it depends upon the chemical, the concentration of the system. How to define a thermodynamic process? See, when I say this system, process, cycle, all, for everything we add a word, the prefix of this word, this thermodynamic. What is a thermodynamic process? What is a thermodynamic cycle? So, process, it is the change undergone by a system from one state to another state, from initial state to final state. It can be in the forward direction or it can be in the reverse direction. The direction could be clockwise as well as the direction could be anti-clockwise. So, any process if you take, it consists of an initial state, like for example, suppose if we take a process 1 to 2, initial state let us take 1, 2 will be the final state, and there will be a series of states in between the initial state and final state. That is called the path. That is the path which connects the initial state and the final state. For example, see, I have plotted a process on a temperature entropy diagram. This is the initial state. Here the process starts at 1 and the initial state of the process is 1 and the final state is 2. This is the final state. So, it is like this process 1 to 2 is perpendicular to x-axis. X-axis we have the property entropy. So, S1 is equal to S2 entropy, and y-axis we have the temperature. So, corresponding to state number 1, initial state, I can read the temperature T1, and corresponding to state 2 we can read the value of temperature 2. And this line from 1 to 2, there is a line, there is a series of state. So, this is the path of the system. So, I have mentioned with an arrow mark. So, this is the path when the process takes place from initial state 1 to final state 2. So, to summarize this concept, a process consists of initial state. In this example, it is state point 1, the final state is state point 2, and the path is from and the line which connects between 1 and 2 is the path of the process. Then how a thermodynamic cycle differs from a path? Series of differs from a processes. Path is the one which connects the initial state with the final state. So, a thermodynamic cycle refers to a series of processes. There is one condition that has to be met, that the initial state and the final state should be the same. That means, wherever the process has started, it has to reach at that point. That the initial state of the cycle and the final state of the cycle should be the same point. In order to have a thermodynamic cycle, minimum 2 processes are required. We cannot have one process and call it as a thermodynamic cycle. So, minimum 2 processes are required to have a thermodynamic cycle. It could be 3 processes, more than 2 is permitted, 4 processes. Most of the thermodynamic cycles, the air standard cycles or power cycles or refrigeration cycles, all these cycles have 4 processes. Generally, they have 4 processes, 1 to 2, 2 to 3, 3 to 4, and again it will be back to 4 to 1. So, the initial point and the final point will be the same. So, here I have taken one example. For example, here it is I have taken a thermodynamic cycle which consists of 4 processes. 1, 2, 3, 4 are the 4 states. 1 to 2 is one process, 2 to 3 is another process, 3 to 4 is another process, and 4 to 1 is another process. So, if you see, there are 4 processes, 1 to 2, 2 to 3, 3 to 4, 4 to 1. So, these 4 are called individual processes. When I combine all these things, 1 to 2, 2 to 3, 3 to 4, 4 to 1, it is referred to as a thermodynamic cycle. So, here if you see, the initial state is 1, the final state. So, as the cycle starts, 1 to 2, 2 is one state, 3 is one state, and 4 is one state. Again from 4 the system is coming back to the initial state. So, here the initial state and final state is 1. One is the initial, and suppose if I assume 1 as the initial state, it is the system is coming back to the original position, which is state point number 1. So, this is the very important condition that has to be met when we define a thermodynamic cycle. Suppose if we have 1 to 2, 2 to 3 and 3 to 4, the initial state is 1, the final state is 4, then we cannot say that it is a thermodynamic cycle, because it has not met the condition that the initial state and the final state should be 1. Now, we are going to see the zeroth law of thermodynamics. See, this zeroth law of thermodynamics forms the basis for temperature measurement. It forms the basis for temperature measurement. Actually, this zeroth law was formulated after the first and second law of thermodynamics was formulated. So, that is why it is given the name zeroth law. Initially, they developed the first law of thermodynamics, then the second law of thermodynamics, comprising of 2 statements, Kelvin-Planck statement and Clausius statement. So, then only this zeroth law of thermodynamics was formulated. So, what does it states? So, let us take 3 bodies or 3 objects A, B and C. If object A or body A is in thermal equilibrium with B, that means A and B has same temperature. As you just saw little before, thermal equilibrium refers to the state where the temperatures are same, that does not change. And if object A, body A is in thermal equilibrium with body B, and B is in thermal equilibrium with C, that means body A will be in thermal equilibrium with C. Let us see here. See, here A is in thermal equilibrium with B, A is in thermal equilibrium with C. If these 2 are in thermal equilibrium, then body B will be in equilibrium with each other. Body B will be in thermal equilibrium with C. or it can be other way. If A is in thermal equilibrium with B, B is with B, C, then C will be in thermal equilibrium with A. It can be in any order. So, this is similar to like in mathematics. If A is equal to B, A is equal to C, then obviously B will be equal to C. B will be equal to C. So, this is simple, just to make you understand easily, I have given this mathematical expression. So, let us take one application of zeroth law of thermodynamics, which is, as I said before, which forms the basis for temperature measurement. So, here I have considered body A, whose temperature is measured by a thermometer. Let us take, for example, the temperature of body A is 35 degree centigrade. So, this temperature of body is measured by the thermometer. The thermometer is considered as the body B. If I say A is in equilibrium with body C, body A and body C are in equilibrium, that means this temperature of this body, temperature of body C will be also equal to 35. Whatever the temperature of body A, that will be the temperature of body C. Because when we say A and C are in thermal equilibrium with each other, so whatever the temperature that is possessed by the body A will be the same temperature of that body C. And here I am considering body B as the thermometer. Now let us move on to the first law of thermodynamics. There are two cases here which for which the first law of thermodynamics can be applied. One is for a change of state, for a system undergoing a change of state. Another one is for a system undergoing a thermodynamic cycle. Let us first let us see what does this first law of thermodynamics says for a closed system which is undergoing a cycle, thermodynamic cycle. So, here I have considered a system which is a closed system, that is control mass. Yesterday we have seen the types of system: open system, closed system and isolated system. Open system is the one in which both mass transfer and energy transfer is there. So, here there is the system is separated from the surrounding. This is the boundary, this is the boundary. Okay. So, this is the surrounding, anything external to the this is the system, anything external to the system is the surrounding, and the boundary separates the system from the surrounding. Let us take a process 1 to 2 or 2 to 1. W1 to 2 is the amount of work transfer or work done on the system, and Q2 to 1 is the amount of heat transferred from the system. Now, whatever the amount of work that is transferred from during this process 1 to 2, it is proportional to Q, the amount of heat transferred during the process. So, W1 to 2 is proportional to Q2 to 1. In order to remove the proportional term, we have to introduce a constant. That constant is called Joule's equivalent or mechanical equivalent of heat. Because here W is the work, Q is the heat, the unit for both, the SI unit for both is joules, and J is the equivalent, Joule's equivalent or mechanical equivalent of heat. So, this is for if I have one work transfer quantity and one heat transfer quantity. Suppose if I have multiple heat transfer and multiple heat and multiple work quantities, that means this, instead of W1 to 2 I can write sigma W, cyclic integral of W will be equal to J into summation of Q cyclic. That is, the cyclic integral of work done by the system will be equal to the cyclic integral of heat added to the system. Okay. The work done will be equal to cyclic integral of heat added to the system. This is suppose if you have 3 work quantities and 3 heat quantities. So, totally there will be 6 quantities plus this joules equivalent term will be there. So, this is for a thermodynamic system undergoing a cycle, because thermodynamic cycle involves a series of processes, minimum 2 processes, maximum we can have n number of processes, we can have any number of processes. So, minimum 2 processes are required to constitute a thermodynamic cycle. Now, for a closed system undergoing a process, so again here I have considered a system where there is one, when we say process, it could be only one, we can take only one process, like there is one heat quantity and one work quantity, and this is the boundary of the system. It is an imaginary one, which is not a visible one, and the system is separated from the surrounding by the boundary, and surrounding refers to the region which is outside the system, So, here Q is the amount of heat added to the system and W is the amount of work done by the system. So, before seeing what are the equations, you should keep in mind, if heat is added to the system, then it is positive. If heat is removed from the system or heat is lost from the system, heat is lost by the system, it is negative sign. Work done by the system is positive and work done on the system is negative. So, here if you see heat is added, so it is a positive quantity, and work is done by the system, so that is also a positive. So, the amount of heat supplied is used by the system to produce useful work. If all the heat is converted into useful work, if all the heat supplied to the system is converted into useful work, that means there is no loss or all the input has been converted into useful output. That means Q will become equal to W. However, in real time applications, all the heat cannot be converted into useful work. So, the difference between Q and W, that is between heat supplied and the work done by the system, is equal to the internal energy of the system, which is represented by delta E. So, rearrange this equation, bring this Q term to the right side, so it will become Q equal to W plus delta E. So, if, as I said a little ago, if the entire heat has been converted into useful work, then delta E is equal to 0. That means the system has got 100% efficiency. Output by input, output is work done, input is Q. So, if you convert equal entire amount into useful work, so the efficiency is 100%. Again, a system undergoing a change of state, if there are more heat and work quantities. So, here I have taken 3 work quantities, 1, 2 and 3. Here W1 is the arrow mark is towards the system, and W2 and W3 the arrow mark is away from the system, pointed away from the system, and there are 2 heat quantities, total 5 quantities are there. Q1 is into the system and Q2 is from the system. When you say, so this heat is added to the system, so heat is added to the system is positive, heat is removed from the system is negative, work done on the system is again negative, this is work done by the system positive, and this is work done by the system again. So, if you see Q1 is positive, Q2 is negative. So, I have written Q1 minus Q2, which is equal to, there are 3 work quantities, W2 and W3 are positive, and W1 is negative. So, I have written here. So, Q equal to W plus delta E, and the difference between the heat supplied and the work done, work quantity, will be equal to the internal energy of the system. This is to explain you with a very simple example. So, if you take the human body, so we take food, our input to the body is the food, which contains the chemical energy present in the food is converted into useful work. We do some work and some amount of heat is lost to the surrounding. It is rejected through in the form of sweat or whatever it is through the skin of our body. So, the difference between these two is the energy which is stored by the food which is inside our body. So, here also we easy example that we can correlate the first law of thermodynamics is our human body. There are three quantities: Q is there, W is there, and the amount of energy stored within the body delta E. So, in the equation Q equal to W plus delta E is the total specific energy. Sometimes this E is replaced by the letter U. E is replaced by the letter U. When we say E, normally though it is called as total specific energy of the system, most of the cases the potential energy and kinetic energy are negligible. So, E becomes U. U is the internal energy. So, that is why I refer to it as internal energy and not energy. So, E is it is a summation of potential energy plus kinetic energy plus internal energy plus flow energy. If potential energy, kinetic energy are negligible, then it becomes E equal to U plus PV. What is U plus PV? U plus PV is nothing but enthalpy. U plus PV is nothing but enthalpy. So, potential energy is, we know, mgz for a unit mass flow rate of the fluid. For a unit mass flow rate of the fluid, m is equal to 1. So, mgh or mgz becomes gz. Kinetic energy is half mv square. If we put m equal to 1, so v square by 2 or half v square, and this term is the enthalpy. This term is the enthalpy. H is equal, U is the internal energy, P is the P is the pressure, and V is the volume, PdV. Yesterday we saw the work done for a constant one of the constant pressure constant process, P for a constant pressure process, integral PdV. dV, if you integrate, you will get V, P into V, integrate, apply the limits between state 1 and state 2, we got P into V2 minus V1. So, based on the concepts that we have seen so far, let us solve some numerical questions. First question is, a rigid tank containing a hot fluid is cooled while being stirred by a paddle wheel. Initially, the internal energy of the fluid is 800 kilojoules. During the cooling process, the fluid loses 500 kilojoules of heat and the paddle wheel does 100 kilojoules of work on the fluid. Determine the final internal energy of the fluid. Neglect the energy stored in the paddle wheel. So, this is the question. So, let us solve this problem. It is a very simple problem. So, this is based on the first law of thermodynamics for a system which undergoes a process. So, this is the system. Here I am considering a tank. A tank is containing a fluid. So, let me draw this one. So, a tank is containing, so this is the tank. So, this is a tank which is containing a fluid. So, the tank is considered as the system. Okay. So, let us write the given data. Initially, the internal energy of the fluid is 800 kilojoule. The initial internal energy is given as 800 kilojoule. So, that means U1 is equal to 800 kilojoule. Internal energy is represented by the letter U. We use H for enthalpy, S for entropy, V for specific volume, U we use it for internal energy. So, this is U1 is equal to 800 kilojoule. During the cooling process, the fluid loses 500 kilojoules of heat. So, there is a loss of heat, there is a loss of, so the fluid is losing 500 kilojoule. Okay, so there is a minus sign because heat is lost. Okay, so I am representing it with the minus sign. There is a work done there's a work, the paddle wheel does a work of 100 kilojoules of heat. So, work is done on the system. So, it is minus 100 kilojoule. The fluid is contained in the tank, which is in the system. Work is not by the fluid, work is done on the fluid. So, work is done by the system. Work done by the system is positive, work done on the system is negative. Similarly, heat added to the system is positive, heat lost or removed from the system is negative. So, let us write the given data. Whatever I have mentioned in the pictorial representation, Q equal to minus 500 kilojoule and W is equal to minus 100. Applying the first law of thermodynamics for a system which is undergoing a process, Q is equal to W plus delta E. If we neglect the other changes in energy like potential energy, kinetic energy. So, this is equal to W plus delta U. So, Q is equal to W plus delta U is U2 minus U1. If we see the question, determine the final internal energy, neglect the energy stored in the paddle wheel. So, the total energy of the system is the, though it is a summation of the other forms of energy, since other energies are neglected, the total energy of the system is equal to the total internal energy of the system. So, we have to find out U2, we have to find out what is the value of U2, what is the value of U2. So, substitute the value, Q is minus 500, U is minus 100. Again let me emphasize, the work done on the system is negative sign, work done by the system is positive, plus U2 is unknown and U1 is 800 kilojoule. So, if you simplify this one, this 800 will come, 800 minus 500 is 300, 300 minus of minus 100 is 400. Therefore, the final internal energy of the fluid is, let me write it again, the final internal energy of the fluid is 400 kilojoules. So, determine the final internal energy of this one. So, when we solve, the final internal energy of the fluid is 400 kilojoules. Now, let us move to the numerical question number 2. A stationary mass of fluid is compressed without friction from an initial state of 0.3 meter cube, that is initial volume is given, pressure is 0.1 megapascal to a final state of 0.15 meter cube, and the pressure is also same. See, if you see the pressure here and here, it is same. That means the process is a constant pressure process. There is a transfer of 37.6 kilojoules of heat from the gas during the process. How much does the internal energy of the system gas change? So, I have a piston cylinder which contains a gas. The gas is considered as the system. The piston cylinder is doing some amount of this one, work is done on the system. So, there is a heat loss of 37.6 kilojoules. So, initial volume is V1 is 0.3 meter cube, final volume is 0.15. We know as the compression, during the compression